Hi students, in the last class we have discussed about standard hydrogen electrode and determining the standard reduction potentials of various electrodes as well as electrochemical series and its applications. And in today's class, that lecture number 4, will start with some problems based on electrochemical series. Yeah, but before that we'll recall once again electrochemical series. Electrochemical series is nothing but the arrangement of various elements in the increasing order of their standard reduction potential values. In that series, fluorine highest SRP value and lithium is the lowest SRP value. Because of higher SRP value, our fluorine acts as a strong oxidizing agent. Therefore, oxidizing power is directly proportional to SRP. Next, lithium because of lesser SRP value acts as a strong reducing agent. Therefore, reducing power is inversely proportional to SRP values. Of course, this concept we have discussed in the last class. Now we will discuss about some problems based on our electrochemical series applications. Question number 1. Can we stir aqueous solution of copper sulfate with a zinc rod? Means, say for example, it is aqueous copper sulfate solution. Aqueous copper sulfate solution, and with the help of a zinc rod, is there any possibility to stir? Is asking that. But answer is no. Why it is not possible? See here, what happens, we'll discuss that. When a zinc rod is used to stir the copper sulfate solution, and zinc being less SRP value and displaces more SRP copper. Zinc being less SRP will come and displace more SRP copper and converted as zinc sulfate, copper will come out. That's why zinc will not used to stir copper sulfate solution. And second question. Here X value, Y value, Z value. 3 different electrodes standard reduction potentials as given. Sir, where the word SRP has given means in electrochemistry, SRP, SOP words have not given, means we have to assume as SRP only. Here SRP of X, SRP of Y as well as SRP of Z has given, and asking order of reducing power. Reducing power is nothing but reducing others itself undergoes oxidation. Reducing others itself undergoes oxidation. Then which element oxidizes easily? Means whose SRP value is very less undergoes oxidation easily. Then out of these 3, Y SRP value is very less. That's why Y undergoes oxidation easily. Then after Y we are taking Z, then we are taking X. This is the order of reducing power. Reducing power means which reduces others itself undergoes oxidation. Y undergoes oxidation easily because its SRP value is very less, and X SRP is more, that's why its reducing power is less. And the third question is then E naught value of chromium plus 3 oblique chromium, and E naught value of Cr2O7 minus 2 oblique Cr plus 3, E naught value of MnO4 minus oblique Mn plus 2, and E naught of chlorine oblique Cl minus has given, and asking which is strongest oxidizing agent. Oxidizing agent always oxidizes others and itself undergoes reduction. Then the reduction purpose, its SRP value should be high. Then out of given electrodes, whose SRP is very high? Then E naught MnO4 minus oblique Mn plus 2, SRP value is very high. That's why comparing with others, and this electrode undergoes reduction easily. And one more important point is all are SRP values only. How we are telling all are SRP values? Because Cr plus 3 converted to Cr0 elemental state. Decrease in oxidation state, absolutely it is reduction process. That's why it is a standard reduction potential only. Here also Cr2O7 minus 2, here chromium oxidation number is plus 6, has converted to plus 3, decrease in oxidation state, reduction only, SRP value. Here also MnO4 minus, manganese oxidation number is plus 7, converted to 2, decrease in oxidation number, again SRP only. Here Cl, then elemental state 0, converted to minus 1, decrease in oxidation state, that is also SRP only. That's why he is asking a strong oxidizing agent. Oxidizing agent oxidizes others, itself undergoes the reduction. Itself undergoes reduction means whose reduction potential is more, that electrode undergoing reduction. Then here comparing the others, this SRP is more. In this process, then which species is undergoing reduction, which species is undergoing oxidation, again very important. That's why we will write clearly MnO4 minus has converted to Mn plus 2. MnO4 minus oxidation number is plus 7, has converted to plus 2. Plus 7 converted to plus 2 means MnO4 minus itself undergoing reduction, remember. MnO4 minus itself undergoing reduction, that's why MnO4 minus is the strongest oxidizing agent in this question. Our answer is MnO4 minus, that's all. Because MnO4 minus, being a plus 7 oxidation state, it is converted to plus 2, decrease in oxidation state, undergoing the reduction. That's why it is a strong oxidizing agent. Alright, these are some questions related to electrochemical series. Next, we'll discuss about one important concept, that is Nernst equation. Nernst, Nernst equation for particularly single electrode potential. Single electrode potential, that is nothing but for E. Nernst equation for single electrode potential. Right, before we'll going to discuss Nernst equation, first we'll discuss some important points. That is E naught Zn plus 2 oblique Zn value minus 0.76 volts. Zinc standard reduction potential value this much. Standard reduction potential value we are telling means here its concentration should be, whose concentration, Zn plus 2 concentration should be 1 molar, it is fixed. And 1 molar concentration only this potential has measured. Exactly E naught Cu plus 2 oblique Cu, that is a plus 0.34 volts. Here also Cu plus 2 concentration is 1 molar. That's why whatever the standard reduction potential values are there, all standard reduction potential values are measured at 1 molar concentration only. Now question arises, instead of 1 molar, if I taken Zn plus 2 concentration has taken 0.1 molar, 0.1 molar concentration has taken, then what is the electrode potential value? Here also Cu plus 2 concentration is not 1 molar, Cu plus 2 concentration is suppose 0.05 molar. Then what is electrode potential value? Then don't say 0.1 also minus 0.76. Here also 0.05 also 0.34 is wrong. Then whatever the values you have mentioned, they are fixed. They are absolutely for 1 molar concentrations purpose only. Other than 1 molar concentrations are given in the solution. Okay, other than 1 molar concentrated solutions are given. Then electrode potential values, how to calculate is the question mark. For that purpose, Nernst has given one equation, nothing but one formula. Based on that formula, will calculate that means single electrode potential values other than 1 molar concentration. We'll see them. For that purpose, one general reduction reaction I am giving, M plus N electrons gives M. Because According to Nernst equation also, we are calculating a reduction potentials only. Of course, they are not standard reduction potentials, but they are reduction potentials. Because other than 1 molar concentration. That's why I am using here one reduction process has given, one general reduction reaction has given. In this, we can also write like this: M plus N, we can call it as a oxidized state. Oxidized state it is. And this is a reduced state. Reduced state. Yeah, what is the meaning of oxidized state and what is the meaning of reduced state? Oxidized state is obtained after oxidation process and reduced state is obtained after reduction process. Or we can also say reduced state is nothing but it is a product. And oxidized state is nothing but it is a reactant. Any word we can use. In the Nernst equation formula, we can use reduced state word or we can also use product. We can use oxidized state word or we can also use a reactant term, anyone we can use. And compulsory we have to take a reduction reaction only, a very important point. Because Nernst equation for single electrode potential. Single electrode potential means which potential? Single reduction potential. That is very important. Whatever the formula we are taking, we are deriving here, that formula is exclusively to calculate reduction potentials only. Okay? Right. Now, we'll write its clear formula, clear explanation we'll see now. Once again, I'll write here M plus N electrons gives M. And it is a, of course, a reduced state, and it is oxidized state. Now first we'll take a Nernst basic equation. Is like this: E M plus N oblique M is equals to E naught M plus N oblique M minus RT by NF ln. Now here we can write like this: reduced state concentration divided by oxidized state concentration. Or instead of reduced state by oxidized state, we can also write like this: or it is nothing but product concentration divided by reactant concentration. Like this also we can write. It is Nernst basic equation. For this purpose there is no any proof then. We have to use directly this formula only. Now this formula we are expanding. Okay. E M plus N oblique M is equals to E naught M plus N oblique M minus RT by NF ln nothing but log base E. This log base E will convert it to log base 10. We will have the relation then. Ln is equals to 2.303 log base 10. Now we will substitute there. Therefore, that 2.303 I write first 2.303 RT by NF. Instead of ln, we will write a log base 10. Now we can use this one or that one, doesn't matter. Now otherwise we will substitute here these values then. Reduced state is nothing but M, metal concentration, divided by oxidized state, nothing but that is a reactant concentration is M plus N. That's all. Right. Now 2.303 RT by F value, these are always constants. They will not change. Therefore 2.303 RT by F values if you substitute, that is 2.303 into R value 8.314 into T value 298 divided by 1 Faraday is nothing but 96,487 coulombs. If you calculate all these values, you will get 0.059. Therefore, we can directly substitute this value here. we'll get a Nernst final equation for single electrode potential. E m plus n oblique m is equals to E naught m plus n oblique m minus instead of this value we'll write here 0.059 by n log base 10 m by metal ion, but the thing is metal being a solid, its molar concentration is 1 unit. That's why 1 by metal ion we can take them. 1 by metal ion. This is final Nernst equation to calculate single electrode potential when concentration is other than 1 molar. If a concentration is 1 molar, already standard electrode potential. We have calculated with the help of SHE. Yesterday in the last class we have discussed that. This is Nernst equation. Based on this Nernst equation, now we will discuss some questions. Once again, here it is a single electrode potential, standard electrode potential, n number of electrons involved in the process, and it is a metal ion concentration. Right. Based on this formula, we'll solve some questions. But before that, it is one general reduction reaction. It is oxidized state. By taking n electrons converted to metal, it is a reduced state, or we can also say product. It is a reactant, and it is a Nernst basic equation. That is a E m plus n oblique m. It is a reduction symbol. Okay, because we are calculating reduction potentials only. It is E naught minus RT by NF. Ln nothing but log base E, reduced state by oxidized state, or we can say product by reactant concentration. Therefore, if you substitute these values here, and at the same time a ln, nothing but log base E also we can convert into log base 10 by multiplying with the 2.303. Then if you simplify all these values, metal concentration is 1, we will get finally Nernst equation like this. It is a single electrode potential, standard electrode potential, it is a metal ion concentration, and it is a number of electrons involved in the process. Right. Now we'll solve some questions based on this Nernst equation. Question number 1. Copper, of course, copper rod is dipped in 0.1 molar aqueous copper sulfate solution at 298 kelvins. Calculate electrode potential and a given value, given E naught Cu plus 2 oblique Cu is equals to plus 0.34 volts. So this is the question. Right. First we will try to understand. It is a copper sulfate solution. In that copper sulfate solution, and whose concentration is of course 0.1 molar, not 1 molar. And in that copper rod has dipped here. Here, after dipping copper rod, how much potential will be generated? How much potential will be developed? That is asking them. And don't tell 0.34. 0.34 potential will be developed when 1 molar copper sulfate solution has used. But it is not 1 molar, it is 0.1 molar. In this case, how much electrode potential will be generated? We'll see now. Answer. Then here 0.1 molar aqueous copper sulfate. 0.1 molar CuSO4, nothing but Cu plus 2. CuSO4 contains Cu plus 2 ions as well as SO4 minus 2 ions. Both concentrations are same, 0.1, 0.1. Now I am using the Cu plus 2 concentration is 0.1 molar. And of course SO4 minus 2 also 0.1 molar only, no doubt in that. And next E naught value. E naught Cu plus 2 oblique Cu is already given 0.34 volts. But what we have to calculate? We have to calculate, it is a standard potential. We will calculate a single electrode potential ECU plus 2 oblique Cu is question mark. For this purpose, we'll use our Nernst equation. That is ECU plus 2 oblique Cu is equals to E naught Cu plus 2 oblique Cu minus 0.059 by N log base 10 product by reactant or reduced state by oxidized state. So here what is reduced state, what is oxidized state, or what is product, what is reactant? Very simple, we have to write its reduction reaction Cu plus 2 by taking 2 electrons converted to Cu. Compulsory the reaction should be reduction reaction. Then it is a product, nothing but reduced state. It is a reactant, nothing but oxidized state. Product by reactant or metal concentration. Product, that is metal concentration is always 1 by Cu plus 2 we can take. 1 by Cu plus 2 concentration. Done. E naught value 0.34 minus 0.059 divided by N value. N value clearly indicating here Cu plus 2 to Cu. How many electrons are involved? I mean just 2 electrons are involved here. Log base 10 1 by Cu plus 2 concentration is 0.1 molar. It is not 1 molar. It is 0.1 molar. Therefore 0.1. 0.34 minus, if you divide this value, you get 0.0295 log base 10, 0.1 nothing but 10 to the power minus 1. If you shift in the numerator, it becomes a 10 log 10. 0.34 minus 0.0295 log base 10 value is 1. And if you subtract these values, you will get 0.31 volts. See here, if a 1 molar concentration, if you maintain, 0.34 is your answer. If a 0.1 molar concentration is maintained, 0.31 is our answer. Okay, this is the electrode potential when 0.1 molar concentration of copper sulfate is used. That's it. Okay, based on the given data, we have calculated electrode potential, that is a single electrode potential of copper when 0.1 molar concentration is used. Suppose here a Cu plus 2 concentration given 1 molar only. Just imagine, suppose. Then what happens? 1 by 1 1 log 1 0 0 into something 0. This part completely becomes 0. In that case, what happened? Single potential, standard potential both becomes equal. If the concentration is 1 molar, single electrode potential as well as the standard electrode potentials becomes the same. But here concentration is 0.1, that's why single potential and standard potentials are not same. Okay, one is 0.34, one is 0.31. Right. Now we will discuss one more question, then we will stop. Next question is, zinc rod. Zinc rod is dipped in 0.1 molar solution of ZnSO4. The salt is 95% dissociated. 95% dissociated, and of course at 298 kelvins. Calculate electrode potential, question mark, and at the same time he has given the E naught Zn plus 2 oblique Zn value, that is a minus 0.76 volts has given. That's all. See the question here, zinc rod, it is a zinc sulfate solution. Zinc sulfate solution concentration is 0.1 molar. In that a zinc rod has dipped, and but the condition is, the important point is, zinc sulfate solution concentration is 0.1 molar. There is no doubt in that. But the thing is, the salt is 95% dissociated. Means this zinc sulfate solution is not dissociating 100%. If a zinc sulfate solution 100% dissociated, then we can take like this. Whatever the zinc sulfate solution concentration is there, nothing but Zn plus 2 also we can take 0.1 molar. When if it is 100% dissociated. But here it is not 100% dissociated. That's why in this case we cannot take directly 0.1. It is just 95% only dissociated. Here we will use one formula which we have learned in the first year equilibrium topic. That is concentration is equals to C alpha. C nothing but given concentration 0.1 and alpha is nothing but degree of dissociation. How much dissociation is taking place? 95% dissociation is taking place. Therefore, we will write here clearly answer. We will write equation as it is Zn plus 2 electrons converted to Zn. I have given here reduction reaction only. It is the oxidized state, a reduced state or product as well as a reactant. Then Zn plus 2 concentration is equals to 0.1 into 95% only dissociated, इसलिए 95 by 100. This is nothing but a C alpha formula. Okay, if it is 100% dissociated, 100 by 100, same 0.1 only will be there, but it is just 95% only, 95 by 100. If you simplify this value, you will get 95 into, if you bring in the numerator 10 to the power of minus 2, already 10 to the power of minus 1, 10 to the power of minus 3 molar. Here as Zn plus 2 concentration, we have to take this much. Don't take 0.1 molar because 0.1 molar concentration is for 100% dissociation. But this is just 95% only dissociated. That's why Zn plus 2 concentration is 95 into 10 to the power of minus 3. And of course, N value is 2. We can write here N is 2. And I will write here E Zn plus 2 oblique Zn is equals to E naught. Zn plus 2 oblique Zn minus 0.059 by N log base 10. Log base 10 product by reactant 1 by Zn plus 2. 1 by Zn plus 2. Concentrations. We have to write square brackets concentrations. Next we are calculating single potential. And standard potential value already given in the question only minus 0.76. Minus 0.059 by N value. Number of electrons involved here are 2 log base 10 1 by Zn plus 2 concentration is 95 into 10 to the power of minus 3. That is nothing but minus 0.76 minus, and if you divide this value 0.0295 log base 10, if you bring in the numerator 1000 divided by 95 minus 0.76 0.0295 log base 10. If you do the simplification, 1000 divided by 95, its value is 10.5. And how to see the log values we have learned in the first year equilibrium topic. Again, now here I cannot explain how to see log values in this live classes. Then in first year, whatever we have learned regarding logarithm problems, once again you just refer those problems. And now if you see log 10.5, see here minus 0.76 minus 0.0295 log 10.5 value. Log 10.5 value 1.022 log 10.5 value, and if you simplify the value, if you do simplification, you will get E naught Zn plus 2 oblique Zn value minus 0.79 volts. If you do the simplification, you will get a minus 0.79 volts. Means if the concentration is 1 molar, the value is minus 0.76. If the concentration is other than 1 molar, other than means its concentration is 95 into 10 is to minus 3 molar, then value is minus 0.79 volts. Okay? Still some more problems are there. I will continue in our next video. Thank you. Bye.